Hey, welcome back. So today we'll be looking into chapter 15 on thermodynamics. Last two chapters, we look at ideal gas and heat capacity and some topics related to those two. So those are kind of preparation into thermodynamics at the end that we'll be looking at how engines work. Okay, so that's will be some of the topics in this chapter later on. But today we'll be focusing on a few topics here. So the first law of thermodynamics will be first, and then we'll be talking about some simple thermal processes in which we'll mention also the heat capacity for ideal gases. So let's jump in. All right. So over the last a couple of hundred years, our human history, actually overgone rapid change, largely due to the industrialization, thanks to the invention of engines. Okay, so this is a picture of the steam engine was uses to transfer heat to the work. This is one time early pictures, one of the early pictures of the trains. Um, so basically, the engines are using thermodynamics, which will be the focus on this chapter. There are a few laws of thermodynamics. So the first one is basically on the conservation of energy here. So the first law states that a system where heat and work are the methods of transferring energy for a system in thermal equilibrium. So for example, if you have a system, its internal energy, we will call it delta, we will call it U. Then change of internal energy will be due to the heat transfer and the work being done either onto the system or out of the system. Okay, so in this case, change of internal energy then merely comes from the change of heat. If you have heat comes into the system, then Q will be positive. If you have work done by the system to the outside, then this gas will be minus. Okay. You might have seen a different form of first law of thermodynamics, which is defines delta U as Q plus W. In that case, W for the work then will be done by the outside environment, the surroundings to the system instead of the system to the surroundings. But either way, they are the same thing here. Okay. Sometimes you have heat comes into the system. Sometimes you also, at the same time, you will also have heat flows out of the system. So then the difference of these two heat will be the total heat. Okay, so heat of going into the system minus heat coming out of the system will be equal to the total heat on the system. The same as the work turn here. Sometimes you might be having multiple things going on at the same time. The system expands, so then it's doing work to the surrounding, or at the same time, a certain part, maybe the surrounding is pushed in. So then the surrounding is doing the work to the system, which is called W in. So you'll take the difference of the two, and then that's the total work done. But basically, delta U equal to Q minus W. Okay. So which means the change of the energy of the system, internal energy of the system is equal to the heat, the total heat it takes in minus the work it does to the environment. Let's take a look on a quick example here. So it says a diatomic gas does 300 joules of work and also absorbs 2.50 kilojoules of heat. What's the net change in the internal energy of the gas? Okay, so this is a gas system. So then we'll be looking at delta U. We'll be using equation delta U equal to Q minus W. Okay, so let's take a look on that. Set this up. So total change of internal energy delta U be equal to Q minus W. Okay, so it's looking for this, then we can figure out these two. These two are given. So it says the system absorbs 2.5 kilojoules of heat. Okay, so that means it takes in heat, so that's positive. So positive are 2.5 kilojoules. So you would do 10 to the third joules. Okay, so that's the Q term minus it does work. Okay, so this system does work. So minus 300 joules work. So remember to convert kilojoules to joules first in this first term. Okay, so that will give you 2200 joules of energy positive. Okay, so the system actually gains 2200 joules of energy in this case. All right, so that's a pretty simple example. We'll go back to the slide and we'll move on from there. And we'll take a look at a couple quick example here. So for example, if you have another system, um, now in this case, there's multiple things going on at the same time. For the heat, it takes in heat, 40 joules heat, but at the same time, it emits 25 joules of heat outside. So when it's emitting, it's minus. So you add these two together, positive and minus, that gives you 15. And at the same time, it does work, but the surrounding does a 4 joules of work in here. So those two has to be taken out. So then you'll do Q comes from these two will be 15 minus 6. That gives you 9. Okay. Another quick example, if the system gives out 150 joules of heat. At the same time, the surrounding does 159 joules of work onto the system. So then in this case, Q will be minus, W will be minus, but there's a negative sign before that W, so it becomes actually positive. Then it gives you also the net change of internal energy to be 9 joules as well. Okay. All right. Our physical body does the same thing. It takes in heat. For example, if the surrounding is actually having higher temperature, then we'll take in the heat. Or if the surrounding is colder, like in winter right now, so we pretty much give our heat here. And if we are moving, we are doing work to the surrounding. Okay, so in that case, um, but the total change in the internal energy of our body also there's energy comes from the food that we take in. Okay, so hopefully that's keeping us a balance of all this. Okay, so our body heat gives out or takes in minus work and then plus food energy. For plants, it does the same thing here. So it takes in heat from the sunlight, and at the same time make give out heat to the surrounding, and it's growing. So then for some veggies, we actually use them for as food to take in, or some animals takes in those leaves, whatever. So those are the foods. So the energy store, excess energy stored in the form of that. So internal energy, change in internal energy, then in here will be equal to the food stored here. Okay. All right. So since since the Industrial Revolution, we have been using engines to do the work and making machines for the work. Okay, um, so that was actually very shortly after the first law of thermodynamics was proposed. Okay, or discovered, if you want to call it that way. Just only 60 years afterwards. So that was really quick in the sense of the discovery of the theory to its application. So for an engine that we are still using today for a lot of our cars, vehicles, so basically it takes heat, so Q in, and it does certain work, and then it will discard the remaining heat to the surrounding. So that's the full process. Okay, so and the engine will return to its initial state. So for this whole process, the change of the energy, internal energy should be equal to 0 because it now recovers to the original state. Okay, so it goes back in that sense. All right. So um, now I want to point out that So this is how an engine is working and how it does. So there's these three components he takes in, does work to the outside, and then he comes out. Okay. So we have tried in history, like attempt to actually convert all the heat to work, but we all fail because it's not possible to come up with a system that where you do not have excess heat. Okay. So the energy it takes in cannot be 100 converted to useful work in that sense. And this is also another statement of the second law of thermodynamics, which we'll talk about it in the next lecture. All right, and let's move on here. So to look at a little bit detail into cycle of engine. Okay, so the engine takes heat in the form of the combustion heat from the fuel. So it then expanded because there's a lot of heat comes in, it expanded and pushed this piston. So, and then to the motors, so it generate work to drive the wheels. And then after that cycle, now the piston will return to its original position. So then it um, pushes out the excess heat to the surrounding. So, and then returns to initial state, and then comes back in, now takes in the heat for the next um, ignition of the fuel, and the heat takes in from that ignition, and then the cycle repeats. Okay. All right. So to understand the those cycles better, first let's talk about some thermal processes here, which are simple processes that will help us understand the whole cycle. Okay, so these are ideal processes, so which means they happen slowly enough, so then the there's either uniform temperature or pressure exists throughout all the regions of the system at all the time. Okay, so um, for simple processes, isobaric, this is when the pressure is actually constant. Okay, and then isochloric, this is when the volume of the system is constant. Isothermal, that is when the temperature of the system is not changing. Adiabatic, that means there's no heat transfer into the system or out of the system to the surroundings. Okay, so let's take a look at them one by one. First, for isobaric, so it's constant pressure. So in the process, the pressure of the system, so in this case, let's take a look on this. Let's say there's a certain gas that is isolated, enclosed here, but the pressure is constant. So you takes in heat, the pressure is constant, then this will expand. Okay, so in that sense, and if we plot the pressure versus volume graph, so then pressure is constant, volume goes. Okay, so in that case, you can see the pressure is constant, so then the force on the piston will be constant, will be the pressure times the area of this cross-sectional area of this cylinder over here, and it pushes the piston outward. Okay, so the piston would move by a distance of d, so pressure, and then displacement of d, so that means there's work being done. Work being done will be then pressure, force times distance that we learned in physics 1. So work on this piston, which is the outside surrounding, is force times distance. Force is pressure times A. So if you do cross-sectional area times D, that gives you the volume of this expanded portion. So then it's pressure times change in volume, which on the graph here, you can see this is pressure here, constant here, expanding volume from initial volume to final volume delta V. So you can see it's the area of this rectangular. So it's basically the area underneath the pressure curve here in this case. Okay, so then for isobaric process, the work done by the gas to the surrounding or the outside is equal to pressure times delta V, because pressure is not changing, delta V. If the volume of the system expanded, then work is positive. If the volume of the system decreases, which means the surrounding is pushing back or pushing into the system, so then the work done is negative by the system, okay, but by the surrounding is positive in that case. Let's take a look on the example here. It says 1 gram of water is placed in a cylinder and the pressure is maintained at 2.0 times 10 to the fifth Pascal. The temperature of the water is raised by 31 degrees Celsius. The water is in the liquid phase and expanded by a small amount of 1.0 times 10 to the minus 8 meters cubed. Okay. It says find the work done and the change of the internal energy. So it says the pressure is maintained constant. So this is isobaric expansion of this water. All right, it's looking for the work done. So if it's isobaric expansion, we can flip once, slide back. So work done by the system, in that case is the water, then it will be P times delta V. Okay, so we can calculate that directly. Work done from this second example. W then equal to P delta V. This is for isobaric process. Okay. And P is given, delta V is also given. Okay, so let's take a look on that. So P is given as 2.0 10 to the fifth Pascal. So that's in SI unit. Delta V it expand by this small amount times 10 to the minus 8 meters cube, also in SI unit. Okay. So this gives you the work done by this water will be 2.0 times 10 to the minus 3 joules. Okay. And it's asking you to find, secondly, what will be the change in internal energy, so delta U. And that we know from the first law of thermodynamics should be Q minus W, okay? So Q minus W, we have this guy from here. Now we just need to figure out Q, okay? So in the problem, so how do we find out Q here? Q is heat added to the system, okay? In the problem, it says the temperature of the water is raised by 31, okay? So for the heat capacity, in last chapter, we know if heat is added to the system, then it should be equal to mc delta T, right? It gives, in the problem, it gives us this one, delta T being 31 degree. This is a constant, heat capacity constant you can look up. And then by now, if you remember, this is 4186 joules kg degree Celsius or Kelvin. M is given here in the problem, and the first two words, it says 1 gram. So this guy is M is 1 gram, 1G. Okay. So you can calculate Q, then you can calculate that. Okay. So it's MC delta T minus the W we had there. But here, 1 gram, it's not SI unit. So you want to times 10 to the minus kilogram, 2 gram conversion. Okay. Or you can basically just do 1.0 times 10 to the minus 3, convert into kilogram, and then C, heat capacity of water is 4186 kilogram degrees Celsius. Delta T is 31 degrees Celsius. Okay, so because it's changing temperature, so you don't have to convert this into Kelvin because this is referring to delta T already. Now minus the 2.0 times 10 to the minus 3 joules. Okay. So all this together will be about 129.764 joules. Or you can just say approximately equal to 101.3 times 10 to the second joules. Okay, about 130 joules. So that's the change in internal energy. Okay, so isobaric P W equal to P delta V, and then Q, we can use that equation to find it out, MC delta T, okay? All right, let's go back to the slides. All right, so now you don't always have isobaric process, right? So normally your pressure might be changing. So if it changes like this, but we can actually make it smaller, like in small segments of delta V's. Okay, so delta V1, delta V2, etc. And if this is small enough, so the change in pressure you can treat as constant. So then the work done during that small segment will be just the area underneath this rectangular, and then you can add them all up. So this is a kind of mathematical trick. So that tells you that if you can divide this um, big part into as many small numbers as possible, then it actually will um, get very close to the shape of the curve here for these rectangular. They will represent or resemble the shape of this, okay, this curve. So that tells you if even this is not an isobaric process, but the work done by the system can be it's going to be just equal to the area underneath the curve from point A to B or from point B to A, whichever way the process undergoes. All right. Next, let's move on to the second process, which is called isochloric process. So that refers to when the volume is constant. So if the volume is constant, then there's no change in volume, even though if you might have force, but that means the volume is not changing. That means displacement is equal to zero. Okay, so in that case, then work done will be equal to zero. So for constant volume, work done is always zero because delta V equal to zero. Change in volume. There's no change in volume. Okay. Um. So in that case, let's take a look at the um a cyclic process over here. So let's say if you have a system starting from point A, B, C, or you can also go from A, D, C in that case. Um, so the work done here, you can divide into, or basically, let's talk about the cyclic or closed path process from A, B, C, D back to A in that case. Okay. So in that case, you can divide the process into two parts from A to B. So that's isobaric, pressure is constant. So then the work done by the process from A to B is the area underneath this um, big line from A to B on this higher line here. So this bigger rectangular shape. From C to D, then it's the area underneath this, but it's going in this opposite way, so it will be minus. Okay. And then from B to C and from A to D is isochloric. Volume is not changing, so these two processes does zero work. So in that sense. So as a result, then if you go from A, B, C, D back to A, then the volume will be these two bigger rectangular plus the small one, but this small one is negative. So then the net result will be just this guy, the area of this closed path, or this one. Okay. So total work done by a cyclic process, in this case, is the area inside the loop. Okay. Now, we knew earlier that it doesn't have to be a flat line on the PV diagram, right? The pressure could vary. So if you have a cyclic process like this, like a oval here, or maybe a circle if you have a circle, or rectangular, or whatever, maybe triangle, what kind of shape you have. Then in general, the work done by a cyclic process will be the area enclosed by the path. Okay. All right. Um, so Next, we'll take a look on an isothermal process. So for an isothermal process, the temperature is not changing. So in that case, if we have a gas as the system, then P will be inversely proportional to volume because this is a constant. Now, these two are also not changing, so those are all constant. So the PV diagram of the PV curves will be parabola curves. Like those one depends on the temperature. You have different shapes of parabola or different curvatures of parabolas. If you go from initial VI to a final VF, okay, if this guy expanded, then the work done will be just underneath the curve here. Mathematically, you can actually show that the work done under a parabola from point 1 to 2 or initial position to final position is going to be equal to nRT times line on the final volume divided by the final initial volume. Or if you use NKT, that's also fine. Work is equal to NKT line of V final over V initial, okay? But you'll need to use calculus knowledge, which will not show the derivation here, but this is the end result, okay? For a isothermal process, if this is ideal gas, then work done by the gas system to the outside is NKT line of VF over VI or nRT of line VF over VI. For ideal gas, if this is isolate system, so for example, if you have this kind of container symmetric each other from left to right, there's a valve in between. If you have a gas initially here, and then this is vacuum, and this is under well insulated, so that means there's no heat exchange to the surrounding, so Q will be equal to 0. In that case, when this valve is open, the gas expand into the vacuum area. So because Q is equal to 0, and there's vacuum initial here, so the gas molecule are actually pushing on nothing here. So there's no work done by the gas molecule. So this kind of expansion is called free expansion. So because there's no temperature changing, there's no Q, so work is also equal to 0 here. So then internal energy change will be equal to 0, okay? All right, because the internal energy of the system, in this case, is solely determined by the temperature of the system, which is related to the movements of all the molecules here, okay? And in the previous chapter, we know that kinetic energy is equal to, of the whole system is equal to 3/2 of nRT, okay? And that we shown earlier. All right. We will talk about equal partition theory here. So for the ideal gas, all the internal energy comes from the kinetic energy, which is 3/2 of nRT. So that's referring to a monatomic ideal gas. In that case, monatomic ideal gas can freely move in X, Y, and Z directions. So then you have 3/2. For each dimension is 1/2 nRT. In that case, now if you have diatomic molecules in the gas instead of monatomic, so in addition to the three translational kinetic energy in X, Y, and Z, the molecules will also rotate. So in this direction and also in this direction. So you add a 2 degree of freedom there. So each degree of freedom has energy of 1/2 of nRT. So then in this case, adding 2, you have then 5/2 of nRT for the internal energy of the whole system. So then for the heat capacity of the gas system, we can still use M mass times C times delta T. Or we can do, we can use moles instead of masses. So because for gases, typically we use moles more than masses. So in that case, then we can also write similar expression Q then equal to MC delta T, okay? And This would be then called the heat capacity or molar heat capacity. C here. Now, typically we use molar heat capacity for two different processes. One is for isochloric, which means volume is constant. So you hold constant volume. So then we use C sub V to denote that V is constant. Or later on, we'll call about the other process called constant pressure, which is isobaric. So then we use C sub P. P then pressure is constant times delta T. So just similar as that because we use moles more often than masses. So then the heat capacity, molar heat capacity of constant volume then will be just Q divided by moles divided by delta T. Okay. So in that case. So if the volume does not change here for constant volume, then there's no work done by the gas, which will be equal to 0. So then Q W will be equal to 0. Delta U then is solely determined by the heat part of the changing heat of the system, okay, which is then 3/2 of nRT for monatomic gas. So therefore, U equal to this guy. So then C sub V is 3/2 of R, okay, because 3/2 of R times delta T to give you Q in that case. All right. Delta U, because the only changing parameter here will be T. So delta U is 3/2 of NR delta T, matching up with this expression. Then you get this C sub V equals to 3/2 of R. For some common gases, it has been experimentally determined that their molar heat capacity for constant volume in the units of R to be for, you can see here, for monatomic gases, there are 3/2, and then for diatomic gases, there are 5/2, and then this is 5/2. This one is close to enough to 5/2, 5/2, okay? And then this guy is also about 5/2, about 2.5. For polyatomic gases, they are more. So 3/2, about 3/2. So this on average, they are about 3/2. Okay. Now for a different process, if the pressure is constant, then we can say Q added or removed to the system is equal to NC P sub P times delta T. So then again, according to first law of thermodynamics, delta U equal to Q minus W. Q now is equal to C times delta T. This is capital C, which means small n times small c here, sub P, okay? So then combine these two equations, C then equals to delta U plus W over delta T, because Q is equal to delta U plus W over delta T. So then for constant pressure, C sub P, you do delta U plus W divided by delta T. For constant pressure, it's delta U plus W. For constant pressure is P delta V over delta T, okay? But for constant volume process, W, because volume is not changing, so W is 0. So then it's just delta U over delta T. So you can see for C sub P and C sub V, if you compare the two, C sub P has an extra term in the denominator. So in general, C sub P is greater than C sub V, okay? And again, mathematically, you can show that C sub P is equal to C sub V plus M times R, but you have to use calculus knowledge, which I will not show the result here in this class, okay? But CP is greater than CV by M times R. All right, here's the table of CP and CV values and the difference of CP and CV. So for monatomic ideal gases, CP will be 5/2 of R, and then CV would be 3/2 of R. So the difference would be 1 R, and then for diatomic, it's the same difference is 1 R. For polyatomic, it's the same as well, okay? All right, let's take a look on this example. So it says a monatomic ideal gas initially at 20 degrees Celsius and 200 kilopascal. Okay, so remember to times 10 to the third for that kilopascal has a volume of 4.00 liter. So liter is not an SI unit. You need to convert it into meters cube. It says it undergoes a quasi-static isothermal expansion. Okay, so isothermal, that means the temperature is not changing. So temperature is still 20.0 degrees. But the pressure reduces to 100 kilopascal. It says first, find the work done by the gas. B, the heat absorbed by the gas during this expansion. Okay, so for isothermal process, work done, we can go back a few slides as a thermal process here. So work done should be equal to nRT line V final over V initial. Okay. So again, we can write that down and then we'll see if we have everything we needed. Okay. So let's switch camera right now. For the third example of the day, work done will be equal to nRT line of V final over V initial. Okay. And let's go back to the problem. Now let's see if we have everything we needed. T, we have it, it's 20 degrees Celsius, but we need to convert into Kelvin. R is the gas constant. And N, we don't have N, it's not given as N. We do not have, or we do have initial volume, we do not have final volume. Okay, so there's a few things we need to figure out. But it says it's ideal gas, so then we'll also write down the ideal gas law here as well. Okay, so it says initially, this guy is 200 kilopascal, and then this guy is V, the 4.0 liters. Okay, so let me write all these down first. 200 kPa VI is 4 liters. Temperature, initial temperature, is 20. Now the temperature initial and final are the same, so we do not have to write like initial and final. Okay, and it says P final is 100 kilopascal. Okay. All right. So first, this guy has to be converted into Kelvin, which is like plus 273.15. Okay. And here, this guy needs to be multiplied by 10 to the minus 3 to be meters cubed. This guy needs to be multiplied by 3 to be in pascals. And then this also multiplied by 10 to the 3 to be in pascals. Okay. So we are looking for this. And we need nRT line of final over initial. Okay. We do have this guy, we do have this guy, we do not have this, and we do have this, we do not have that. Okay. And we can also use this equation. So if we do like initial and initial, they will give us that. So we actually can figure out N and R and T all together. Okay. So then we don't have to figure out N separately because these all three will be multiplied together. So then we can just say, okay, that's PIVI. And PIVI equal to nRT according to that. Now line R V final over V initial. We have V initial. Now can we find our V final if T is constant? So if T is constant for ideal gas law, then these three multiplied should be constant, right? So that means P initial V initial will be equal to P final V final because P times V is equal to nRT. P initial V initial is nRT. P final V final is also nRT. So these two then is the same. So then we can see here if we have this, we can rearrange the terms, right? We can do Pi over P final, and then that should equal to V final over V initial. Okay, basically move this guy to the other side, you'll divide it this side by that. You move this guy to this side, you will divide pi over pf. Okay, so just moving things around. So you can see now we'll have this together, v final over v initial together, which is equal to p initial over p final. So then this here can be replaced by these two because these two are given. So then that equals to pi vi ln of pi over pf. Okay. All right. So then now we pretty much have everything we needed. So 200 kilo PA times volume 4.0010 to the minus 3 meters cubed, and natural logarithm of P initial 200 kilopascals over 100 kilopascals. Okay, so that will give us 555 joules of work. Okay, so work done by the gas will be that. All right, for part B is asking for the heat, Q. What's Q? So according to first law of thermodynamics, delta U is equal to Q minus W. So we have this guy as 555. What's the Q? What's change of delta U? Change of delta U. Now remember this is ideal gas. Okay. And if you go a couple slides back, you'll have to do this on your own, but for isothermal process of ideal gas, let me go back to the slide. Here, for isothermal process, okay, delta U is going to be 0 because U is only determined by T. So if it's isothermal, T is not changing. So then delta U should be equal to 0, okay? So then go back to the problem here, or the example here, our delta U is going to be equal to 0 because this is isothermal process, okay? So this is 0, then Q should be equal to W. Okay, should be equal to 555 joules as well. Okay. All right. So going back. Last, we'll take a look at the process called adiabatic process. So this is the process that there's no heat into or out of the system. There are a couple of ways you can do this. One is you can make the process happen so quickly so there's no time for heat to escape or comes into the system. Or you can have a system that's very well insulated. So no matter how slow the process goes, this is well insulated, so there's no heat exchange. Okay, so those two ways to make this process happen. If you have a diesel engine vehicle, then it's actually having the adiabatic process. So the fuel is going to be compressed quickly and then they ignite the fuel. Okay, so you can search a demo for adiabatic process on YouTube. Probably you can find this, but you can also catch me in the class and then let me do this demo to you. Okay, so basically there's a cotton or a piece of tissue here, and you quickly push this guy down. So it happens so quickly, then there's no heat escaping over here. So the gas here is being compressed. So it takes in a lot of work, and the internal energy of the system increases because of that work added to the system. Now, because there's no time for the heat to escape, so then the temperature of the gas will the system will increase dramatically, and you may be able to ignite the tissue here in the chamber here. Okay. All right. So let's take a quick review on what we learned today. So we learned a couple of things. The first law of thermodynamics, so change in internal energy comes in two ways. Depends on the if you have heat comes in and if there's work done by the system to the outside. So it's heat comes in minus the work done by the system to the surrounding. And we took a look at several simple thermal processes. So for isobaric, and that's constant pressure, so the work done during the process is pressure times the volume change. Isochloric, that is constant volume, so change in volume is zero, so there's no work done equal to zero. Isothermal, so T is not changing, so then delta U goes to zero, so then Q equal to W, okay? Adiabatic, no heat transfers. That means Q equal to zero, so there's no heat transfer. During the discussion of thermal processes, we also talk about heat capacity for ideal gases, which we use molar heat capacity instead of mass heat capacity, like the mass. So we use Q equal to mc delta T. Okay. All right, that'll be it for today. I'll see you guys next time.